UNESP-Araraquara. So she's going to talk about entanglement as witness of quantum phase transitions in one-dense systems. Vivian, please.
Okay. So I would like to thank the organizers for this invitation to be here and talk about some of our recent results. And I would like to register myself to the Boteco da Dona Tati for tomorrow. So count on me. Let me, is it appearing? Oh, here. So today I'm going to talk about how we have been using entanglement to detect and explore quantum phase transitions in 1D systems. And here, right. So here's the outline of the talk. I will give you a brief motivation. I'm trying this side. I will give you a brief motivation and then also describe just quickly the methods we use to quantify these entanglement quantities and then focus on the results, where I intend to show you results on these two distinct transitions, superfluid to insulator transition and metal to insulator transition, both in disordered systems, and conclusions. So it's not really, well, I can also use here in case. Well, when we think about entanglement, first thing that comes to our mind is typically these nice applications in quantum technologies, as quantum computation, quantum cryptography, teleportation. But of course, we also can use this, and it's more recent, but we can also use entanglement to detect or to witness quantum phase transitions with respect to a certain parameter. And to understand why entanglement can be useful in this sense, let's start with the very general definition of entanglement, but it's a very basic one, it's still quite general, but we say that the two parts, A and B of a given system, they are entangled to each other if we cannot separate the total state CAB into the product state of the separate states, CA and CB. So if this condition is not satisfied, then there is some entanglement in there between these two parts, A and B. But this is very, very general. I will be more specific later on. But now notice that here I'm not really defining what is A, what is B. This could be two particles or two molecules, or even two spatial regions of your system, or even two different degrees of freedom of a single particle. So it's quite general up to now. But the point is that if they share this entanglement, it means if we perform a measurement in one of the systems, let's say A, it will affect immediately the state of the other system. And more important than that is the fact that it's not only a question whether you have or not have entanglement in the system, but how much entanglement you have. So there is a certain degree of entanglement, different degrees of entanglement that will be useful for describing quantum phase transitions. And the reason is that in a general way, we would expect that the entanglement behaves very differently in one phase and in other quantum phase transitions with respect to a specific parameter. So that is still very general. So let's start to be more specific to our system. So here, we will look at disordered Hubbard chains. So how we model that in our case, we simply, start with the usual Hubbard model, so no extension for the interaction or the kinetic term. And we plug there a certain external potential in a very specific way, which is the following. We set on-site impurities, so like point-like impurities with a certain intensity VI. And depending on the number of impurities that we plug in the system, so LV is the number of impurities, with respect to the total size chain, we have a certain concentration of impurities in the system. And this will be a key parameter, this concentration of impurities. And what is random here is where these impurities are placed in your chain. So we put there randomly. And of course, we have to perform several samples to vary all the several possible distribution of a certain concentration of impurities along the chain. And then, now what we know, sorry, well, what we know about this system in t equal to 0, what we do have there is a kind of phase diagram that I'm showing to you, but very pictorial. It's just the following. If we discard this external potential, this disorder, if we only have interaction in the system, and if it's repulsive, so here I can treat the metallic phase of the Hubbard model by plugging a positive interaction, or go to a BCS description with attractive interaction. So if I focus on the positive interaction, so the metallic system, even without disorder, we can see a metal to insulator transition by varying the density. So by varying the average density at n equal to 1, that's the metal insulator transition. Now, we also have, for the BCS sides, so if we consider this U, this U is smaller than 0, negative interactions, this is essentially the BCS description. We have some superfluid in principle, but by plugging together with this superfluidity, this disorder potential, we expect to see a superfluid to insulator transition. And now if we go to the, okay, let's start with the no-interacting case. If I have no interacting case, only disorder, this is the Anderson metal to insulator transition. And also, if I consider this repulsive interaction with V, I expect to be in a Mott-Anderson regime, where I can have metal to insulator transitions from both sides, from the interaction and from V, the disorder. So now, our question here is, can entanglement witness this localization phenomenon somehow? And in order to address this question, we first start by defining what we measure as entanglement. So here, what we consider in this chain, in this disordered chain, is what we call single-site entanglement. So what is this? We simply choose one of the specific sites, and that is our part A. And then we calculate the entanglement between this single site with respect to the L minus A sites. When we do that, we have a bipartite entanglement, A and B only. And for the ground state, this bipartite entanglement is well quantified via some of the entropies. And here we are using the linear entropy, which is given by that. Okay? So when I do that, so essentially, that's the definition. I can end up by writing the reduced density matrix of this site in the base of occupation. I can end up with this formula, where this Wi are simply the occupation probabilities of that specific site. So the occupation probability of single particles with spin up, down, double occupation, or zero occupation there. Okay? But notice that when I did that, essentially, it is still very specific which site I have chosen for do this analysis. So that's why we have to do now what we call here the average. We have to simply vary this site and run the entire chain and get an average on that. So now, before I move on, let me just emphasize that, of course, these are probabilities. I could do exact diagonalization to get this reduced density matrix in this occupation basis and get this quantity exactly. It would be possible, but in general, when we are dealing with these several possibilities and concentrations or where to put this disorder, it's more interesting to have larger chains. And in this sense, it becomes more complicated to get these quantities for larger chains. Like here, we are using 100 sites. And also because we also have to consider several samples of these big chains to average the behavior due to specific configurations of impurities. Therefore, exact diagonalization is not the best case because we cannot go much further in size. Also, the MRG might be quite expensive, especially if you have to run several samples. So our methodology, I will try now. No. So our methodology is the dense functional theory here. So I will give you just a very general idea of the method. So we start with the Hohenberg-Kohn theorem, which guarantees that there is a unique relation between the wave function of interacting any particles with the single particle density of the system. And the fact that because of this theorem, all observables are also density functionals. That means, in principle, if we knew this object here, this density functional, for any O observable that you want, and you also knew the density, exact density profile of your disordered system, in principle, this would give us exactly the information of that quantity. The problem is that the Hohenberg-Kohn theorem does not give any hint of how we can get both the density, neither the observable, the density functional for the observable that you are interested on, in our case, the linear entropy. Okay? So the first part was fixed many years ago, almost together with the Hohenberg-Kohn theorem, which is simply the Conchan scheme. There are other ways to do DFT, but this one is some of the most standard approach. And that means what we do in this scheme, we map another map now between the interacting system that I don't know how to solve, or that's very complicated due to the interactions. There is a mapping between, I map this interacting system to a Conchan system, a fictitious, non-interacting system. And this is performed in a way that we force this effective density potential in the simpler case to reproduce the density of the complex system, of the interacting system. How we do that? We simply say that the effective has to be constructed in this way, such that it reproduces this part here. And then by doing this, I end up with only a single particle Schrödinger's equation. And from the Conchan orbitals, if I solve this, I get these orbitals, and I could plug in here and get the density. It seems simple, but the problem is that this quantity also depends on the density. So in the end, what we have is a self-constant cycle. So I have to start here with a certain initial density, a trial, a first initial density, a tentative density for the system. Then I get the effective or Conchan potential, solve the Schrödinger equation, and calculate this density. Then I ask whether it has converged or not with certain convergence, certain criterion for convergence. And if yes, that means we found the density. And if no, I have to restart again. And I may, for example, use this, the output of here as an input for another tentative and so on. So that's the very general idea of how DFT with Conchan scheme works. But the point is, this exchange correlation potential in this case, that is plugging here inside of the Conchan potential is also something that in general we don't know. So it's very tough to start with because we have to approximate this guy with some things depending on the material and the system and so on. So what we do is, in our work, is the simplest approximation possible, which is the so-called local density approximation, LDA. So in general, what we do, we consider that locally, the density varies not much. So we can use information of the homogeneous system, where the density does not vary, locally replacing the density by the real density, by the density of the inhomogeneous system in R, okay? So we use that, but notice that we still have to give some input for this LDA approach, right? And the input is some exact data or some approximation for that quantity in the homogeneous limit. So here we do this as the following. So for the exchange correlation term, we use exact data, but numerical one. So they are the numerical solutions of the Liouville equations for the Hubbard model, 1D Hubbard model. Now for the linear entropy, let me just, and then when we do that for each specific set of parameters, we have to consider 100 samples, and the quantities we obtain from there is an average of these 100 samples. Now for the linear entropy, we do a similar stuff, but as an input of a LDA, now we use an approximate density functional that we have proposed years ago already for the linear entropy. So we also do a kind of LDA approach for the linear entropy, where we use the information that we get in this step, which is the density profile. And from there, we have an approximate linear entropy for the disordered chain. I know it's fast and not much details, but just to give you an idea of how this approach performs with respect to some exact data, I'm here comparing the DFT approach with this LDA, which is the most simple approximation within DFT, with the MRG. So the red dots are the MRG, and the blue line are the DFT with this whole package of approximations and so on. And these are systems that I will describe now in the talk. So we see that our approach is reliable. No, this is already with some, here, for example, is not interacting, but with disorder interaction. So it's already our system. So thanks for asking. Now, so let's start to see the results. So first, we analyze the case where I started with attractive interaction. So I expect to have a BCS superfluid. And then I turn on the disorder strength. And this is my average linear entropy obtained in that way as a function of the disorder strength for several concentrations of impurities. So as we see here for this particular interaction regime, we see that as soon as we turn on the disorder, the entanglement drops a lot. It's about 50%, depending on the concentration. But for all of them, it's almost 50%. We also observe that as we increase further the disorder strength, there is a saturation with V for all the concentrations true. So these two things together, the fact that the entanglement drops a lot and saturates in a certain value, are our signatures that the system is getting frozen. So that means we start with a superfluid at V equal to 0, attractive interaction. We have a BCS superfluid. As soon as I put some disorder strength there, the entanglement decreases a lot, so it may, the quantum states are more defined somehow, certain sense. And when it's frozen, that means there is no further superfluidity there, so we are interpreting this as an insulator phase already, okay? So now here, so in the system is simply very strongly localized dimers, since it's attractive, we have localized dimers in the chain. But the point here is this green curve. First, notice that if we start with the blue one and increase the concentration, it will start to come here from blue to orange to green, and then it comes back, so it's non-monotonic with the concentration. And the green one is the only one whose saturation value of entanglement reaches 0. All the other cases reach some finite value for entanglement. Also, there is something here in the green one for very small external potential, disorder potential, that's not there for the other concentrations. So to try to understand that, let me start with the fact that it reaches 0 by looking at this graphic here. So now, this red curve is the situation I had before. It's for this density. But now I'm varying instead the concentration for a fixed interaction too, but for a fixed disorder strength, very strong disorder strength. So when we see that and vary also the density of the system, we see that that critical concentration that before was here for C equals 40, now depends on, we can clearly see that depends on the density. And we have, and it's possible to check that this special concentration, critical CC that I'm calling there, associated to a fully localized state because entanglement goes to 0. So it occurs when the number of impurities coincides with the number of dimers, with the number of pairs that I have in the system. And then if you just use the definition here, we can get, which is this critical concentration, CC here, okay? And that is what is observed here. And it's very nice because there is a particle-hole symmetry. If you go from attractive disorder, B minus 10, to repulsive disorder, plus 10, we also see this critical, however, in this, with this symmetry. And you can go from one to other by simply doing a particle-hole symmetry for the density, which means replace the density by 2 minus n. Well, now when we now consider the situation of what's happening in the small regime of interactions, here we compare then for that specific case when we have a strong disorder, attractive disorder, or small or weaker disorder. And we see that depending on the intensity of this disorder strength, the minimum does not appear anymore in that critical concentration that we are seeing. So it seems that the system requires a minimum disorder amount to reach that specific fully localized state. Of course, it's localized, but not in this very specific full localization situation. And it can be also seen here when we plug the average probabilities of those systems. So here I show the average probabilities in the impurity sites, which is the red curve, and in the non-impurity sites, which is the blue. And we see that its V is not strong enough. The system always has some non-zero probability of having pairs or of occupying the non-impurity sites. In comparison to this case, that we have a very strong attractive disorder already, and beyond that critical concentration, there is zero probability of finding the pair outside the impurity sites. Well, so this is for the superfluid to insulator transition. Now let's take a look on the metal to insulator transition. And I will start with the simple MOT one. So here there is no disorder. So it's the homogeneous system. Here's the same quantity, the average linear entropy of a single site, the average over all the sites. And now I vary here the particle density, so the filling factor. And as we expect, the maximum entanglement occurs when there is no interaction. So that means we have all the possible 4 states in the most equilibrated way. So there is the maximum there. And as soon as we turn on the interaction, no disorder, but we turn on the interaction, we start to see in the region close to the critical point, to the critical density n equal to 1, the decreasing of entanglement. Yes, not only at n equal to 1, there is a regime where this thing appears, but we start to see a decreasing, indicating we are approaching the insulator phase. And also, and there specifically at the critical n equal to 1, we see a local minimum, again, similar to the other case, but now for the specific critical density associated to the MOT MIT. But interesting, the minimum never reaches the 0 entanglement. So you see, even for infinite interaction, we have some finite value for this entanglement. And that's why we are defining this regime as a kind of partially localized state. From the entanglement point of view, that means that there remains some degrees of freedom in the system that are not frozen out. And that's probably related to spin degrees of freedom that are not affected by the Coulomb interaction. Now we go to the case where we just have disorder, no interaction, just disorder. Here is what we get. So no interaction on some disorder strength there. We observe that that's for a specific concentration. I think it's 50% of impurities. That's why this minimum appearing here. I will show in the next slide. But the point here is that as soon as I turn on the disorder strength, a very small disorder strength, not only a part of this graphic decrease on entanglement, but you see this decreasing, comparing the blue to the orange. We see that this decreasing occurs for any density. But a minimum starts to appear here only, let me just put it there, only for a certain values or intensities of the disorder potential. And that happens more or less here. For v equal to -3, it starts to appear something here, and then you see further this. But in opposition to what we saw for the MOT case, here in the Anderson, we see that the entanglement may reach the 0 value. That means that in this case, for the Anderson situation, we do have a localization everywhere, but for this specific critical density, we reach the full localization, which is essentially a real localized localization of the pairs in the real space. Okay? So now we will consider, great. So that's my, I will skip some of the other results, but I focus on this here. So essentially now, we are plugging the two features, the interaction and the disorder. And we turn on this orange curve with a small intensity -1 with a certain concentration. And well, as we saw in the previous slide, a small disorder does not give that minimum, local minimum. So that happens here too. We don't see the minimum related to Anderson. And the MOT is essentially at the same place. But as I increase the disorder strength, I start to see several things. So first, the minimum at the disorder appears at the proper place. So there's no change on the critical density where this minimum appears. However, we see that it's not 0 anymore even for v equal to -10. So it means that the interaction is requiring a stronger disorder potential to reach the full localization. And we can confirm that by going further on the intensity of the disorder, and we see that we do reach the full localization, but a stronger disorder is required due to the interaction, the presence of interaction. Now, we also look at the MOT. If you focus on the MOT now, what was here now is displaced by a certain factor, and that's the factor, and it's related to effective density phenomena. So essentially, while in the original MOT you have n equal to 1 in the entire chain, now in the presence of the disorder, this happens only in a part of your chain. In this case, since V is attractive, that happens when in the non-impaired sites. And we also see a similar effect here. In this case, it's very small, but this decreasing of entanglement here is also related to this effective density phenomenon. However, it is happening in the impaired sites. So it means that we have a MOT-like situation where we have n equal to 1 in the sites. However, it's not the entire chain. Instead, it is either on the impaired sites or in the non-impaired ones. This is this phenomenon. And that is also the particle holo symmetry. It's very nice to see when you go from minus V to plus V. And well, this is a summary of those critical densities observed here for the MIT. And let me just show this one. I will choose this one. So, to finish. So here we also were considering if there is this interplay of U and V. That means somehow, depending on this interplay, on this intensity of the two phenomena, the two features, interaction or disorder, you may find only one of these localized systems. And that's exactly what we see here. So we see that if you put, if interaction U is smaller than V over 2, we only find the minimum related to the fully Anderson localization, which is this one. Now, if you go to U larger than V, the MOT-like appears, which is these curves here. And to having both the two phenomena at the same system, disorder system, the condition is, the condition is that we have to have this situation. So it's very strong repulsive interaction with V even larger than U, then you find out the two things here, okay? So I think I'm running out of the time. We have just explored the effects of temperature. The fully Anderson localization is more robust against temperature than the MOT-like seems to be. Also some effects of magnetization. But with that, I'd like to conclude. The name of the slide disappeared there. But these are my conclusions. So answering the initial question, yes, we can use entanglement to witness and explore the superfluid insulator transition and the metal-insulator transition in these disordered chains. I would like to thank the people very closely involved in this work. So my former PhD student, who did most of the works, Guilherme Canella, and our collaborator, Christian Zavadsk. Here's just a summary of what we have seen. And this is our research group there at the moment at UNESP-Araraquara. You may recognize some of them here in the event. Not all of them, because the hair are changing all the time and so on. But almost all of them have some posters. So thank you very much for your attention.
So thank you, Vivian, for this nice talk. Questions? Oh.
Thank you, Vivian. I have a lot of questions, but I'm not going to ask all of them. But I have to preach my gospel here. And
I I measure.
localization part of the physics, we know, for instance, that some quantities are not self-averaging when you have disorder. So, for instance, the local density of states is known to be non-self-averaging, and such that the average local density of states shows no sign of localization.
Okay.
And you have to look either at the full distribution or at some quantity like the typical value or geometric average and so on. So you use the average linear density. And for instance, you have things like you have situations where you know the system is localized, for instance, just disorder, and your witness doesn't really go to zero, and I'm afraid that if you look at the full distribution or the typical value, you might be able to see a faithful witness to the localization transition of your system, because this is especially strong in 1D. 1D is the largest case where this effect is very important. So I wonder if you had a look at the distributions of the linear density or at some other thing like typical value of the linear density and so on.
Yes. Well, it's a very good question. Of course, it would be interesting to have these most common signatures to compare with our entanglement measures. But the point is that we are quite limited because of the methodology. So what I get from the DFT are the density profiles, which we try to analyze somehow those probabilities, average probabilities. We are trying to more or less understand how are the distributions in the disorder chains and the total energy. But I disagree a little bit about the fact that we are getting an average quantity, because it's not exactly as the energy that you sum up and get an average or so. The single-site entanglement is really looking at the specific configurations of the system. And I do the average exactly to avoid these specific trends coming from the particular position of the impurities for each specific set of parameters. So it contains a lot of information of this structure. It's not exactly, it's not comparable to an average energy or so. But yes, it would be interesting to see, to compare and to analyze, because you are right. Here at the moment, what our measures are saying is that there are different levels of localization. And that is weird, but that's what we have there.
I guess you agree with me that with your own methodology, you can very easily look at distributions. You don't have to take the average. You have 100 sites, you have 100 linear densities,
yes,
and you can build, and you have different disorder realizations. You can build the distribution of the linear density. It's not hard.
Yes, but do you mean for this specific type of potential, I should do the many samples, right?
Yeah, you have to do different realizations, of course. But even for one single system, you already have a lot of samples, because different sites have different values. So with 100 sites and, I don't know, 100 realizations, you have 10 to the 4th samples to build a distribution with. And with your own method, you can do that. I think it should be interesting to look at that.
Yeah, it's very interesting, and I'd like to talk to you after.
Thank you. I have a couple of questions, actually. It's very interesting work. I have some maybe naive question about how then would this go to 2 dimensions, or how would it change to get to more real systems? And then the second question is maybe even a bit related, but how to choose which entangled states to think about? So charge, entangled, spin, entangled. Is it possible that your results would become different if you looked at different entangled quantities, or is that just a nonsense question? Okay,
well, these 2 are very good questions. So the first one, I have no clue how to extend all this analysis to 2D. and what is the important thing to do, but I have no clue how to do that. And the second related to, it's to the...
What type of entangled state?
Yeah, how we, it's not, with this measure, I cannot, because I'm really looking at the occupation probability, so I cannot really say, oh, this amount is charged, this amount is spin, and so on. I cannot, yes, I cannot really specify which part is from which degrees of freedom.
Okay. So would it be maybe in different systems, it would just turn out? So if you were looking at it, it would just turn out that in the end you would find out that that was
yes,
the charge,
like
or that was
going
the,
to a Heisenberg chains. Yes, yes.
Okay,
Then the way.
So one last question here.
Hi. Do you think it's possible to extend your methodology to different models rather than the Hubbard model?
Well, of course, the general DFT methodology can be extended. Mm-hmm. But if we come back to the methodology, what I had to use there for this specific model is this slide. So what we have to have before starting is some dense functional for the quantity you want to explore. Mm-hmm. So suppose you want to look at single site entanglement 2. Okay, that's fine. But then you have to have for your specific model this homogeneous dense functional for doing a LDA approach. Okay. Exactly the same approach that would be required. You would have to have that.
And from the
either
Hubbard
exact,
model?
It could be exact, experimental, or in our case, some approximation.
Okay. And for the Hubbard model, you know that from
yes,
okay.
Exactly. Mm-hmm.
Okay, thanks.
Mm-hmm. So, okay, so let's thank Vivian again and we move on to the next talk.